Hi all, welcome to another video of electrical machine design. So today we are going to discuss the problems from the synchronous machine modules, that is fourth module of KTU syllabus. So here we will find the main dimensions of an alternator based on the given values. So the first problem is determine the main dimensions for a 1000 kVA 50 Hz 3-phase 375 RPM alternator. The average air gap flux density is 0.55 Weber per meter square and the ampere conductors per meter are 28,000. Use rectangular poles and assume a suitable value for ratio of core length to pole pitch in order that bolted on pole construction is used, for which the maximum permissible peripheral speed is 50 meter per second. The runaway speed is 1.8 times the synchronous speed. So these are the given values, and we have to find the main dimensions of this alternator. Okay, so main dimensions means we have to find the value of capital D and capital L, that is diameter of core and length of the core L. Okay, so that we have to find. So as we know, normally we will be finding the value of D and L from our output equation, that is Q is equal to C0 D square L into NS. Okay, where C0 is the output coefficient and D is the diameter and L is the length, and NS is the speed in RPS. Okay. So before doing the problem, just note down the values given. Okay, here the value of Q is 1000, it is given as 1000 kVA. Okay, and F is 50 Hz and NS is 375 RPM. It is in RPM. Okay, but in our output equation we are using a small ns, which means speed in RPS. So we have to divide this capital NS by 60 to get small ns, that is speed in RPS. Okay, and average air gap flux density, that is it is denoted as BAV, that is our specific magnetic loading. Okay, and ampere conductors per meter, it is AC. Okay, that is specific electric loading. And we are asked to assume a suitable value for ratio core length to pole pitch, and we have to check what type of pole construction is to be used. Okay, so first we are going to find, as we discussed earlier, we are going to find the small ns, that is synchronous speed in RPS. So for finding that, the equation is capital NS by 60. Okay, we know that the capital NS is 375 by 60. Okay, and we will get the answer as 6.25 RPS. Okay, and also we can find the number of poles. Okay, number of poles, we know the relation, that is NS is equal to 120 F by P. Okay, here for finding the number of poles, 120 F by NS, 120 F by NS. Okay, so just substitute the value of F and NS and we will get the number of poles. Okay, so here they have used an equation based on small ns, so P is equal to 2 into 50 by 6.25, 16. Okay, we can use any equation, any method, suitable method. Okay, we can find number of poles from capital NS, that is RPM. Okay, rotation per minute, and also we can find the number of poles P based on small ns, that is rotation per second. Okay, both we can use, we will be getting the same value as P is equal to 16. And here we can assume a winding factor kW. Okay, normally if the value of kW is not given, we are assuming it as 0.995. Okay, 0.9. Normally we are assuming it as 0.555. Okay, here we are taking the value of kW as 0.995. Okay, no problem. because the value is not given, so we can assume a value of winding factor near to 1. Okay, so here it is given as 0.995. Actually we are using it as 0.955. okay, normally we will be taking the value of winding factor KW as 0.955 if it is not given in the question. Okay, 0.955. Of course, that is actually in the equation itself they have used the 0.95, so a small mistake is there. And we can substitute the values in our equation, that is Q is equal to C0 d square L into NS. Okay, so here we can find the value of C0 using this equation. Okay, using this equation, and NS we know, the value of NS we know, and Q we know. So using that we can find value for d square L. So d square L will be equal to Q by C0 and S. So d square L will be equal to Q by C0 and S. So here they have found the value of C0 separately. So for finding C0, it is the equation is 11 kW BAV AC into 10 ratio minus 3, and you will get C0 as 162. Okay, 162, and substitute that values in the d square L equation. Q we know it is 1000 kVA, and C0 it is 162, and NS is it is 6.25. okay, and we will get the d square L as 0.987 meter cube. Okay, all of you try it with your calculator and check whether the answer is correct or not. And here we obtain a value for d square L. Okay, then the next step is to separation of this d and L. Okay, we have to find a separate value for the main dimensions d and L. So for getting that, we can use the pole proportion. In the question itself, they are asked to assume a suitable value for ratio of core length to pole pitch. Core length to pole pitch means that is L by toe ratio. L by toe. Pole pitch is toe. So here we are assuming a value of L by toe as 2. Okay, as 2, and we know the value of toe as that is pole pitch. It is represented as pi d by p, and so L by pi d by p is equal to 2. Okay, L by pi d by p is equal to 2, and the value of number of poles we know. Okay, so we will get a relation between this L and D from this equation. Okay, and we are obtaining the relation of L and D as L is equal to 0.393 D here, and we are going to substitute the value of L in this equation. Instead of this L, we will substitute this 0.393 D, so it will become 0.393 D cube. So 0.393 D cube will be equal to 0.987. From that we obtain the value of D as 0.36 and L as 0.535. Using this relation, we will get the L as 0.535 meter. Okay, and the next step is to find the pole construction we have to use. Okay, so for that we must know the peripheral speed and runner speed. Okay, so the peripheral speed can be found using the equation V is equal to pi d ns, and d we know, ns we know, and we will get it as 26.7 meter per second. And also in the question it is given that the runway speed is 1.8 times the synchronous speed. Okay, so 1.8 times the synchronous speed, so 1.8 into this 26.7. okay, and we will get as approximately it as 48 meter per second, that is below this 50 meters per second, and therefore a simple bolted on pole construction can be used. Okay, if our speed is below 50 meters meter per second, we can use simple bolted on pole construction, and if it is above 50 and below, okay, below less than 80 meter per second, we can use dovetail T-type construction. Okay, and here we are going to use bolted on pole construction. So I hope it's clear, the problem is clear, so do it and try it. And one more question is the find the main dimensions of a 2500 kVA 187.5 rpm, 50 Hz, 3-phase, 3 kilovolt silent pole synchronous generator. The generator is to be a vertical water field type. The specific magnetic loading is 0.6 watt per meter square, and the specific electric loading is 34,000 ampere per meter. Use circular poles with a ratio of core length to pole pitch as 0.65. Specify the type of pole construction used if the runaway speed is about 2 times the normal speed. Okay, the same problem, same model of problem. So first we have to note down the values. Q, capital Q as 2500 kVA. All of you just note down the values. And NS, capital NS is 187.5 rpm. Frequency is 50 Hz. And then other values, the specific magnetic loading BAV is 0.6, and specific electric loading AC is 34,000, and L by tau ratio. Okay, L by tau ratio for the D and L separation, here it is given as 0.65. okay, this is the main values they are given, and we have to follow the same steps as in the previous question. So here first we have to find the synchronous speed, that is small letter ns, that is to substitute in our output equation Q is equal to C0 D square lns. This is the starting equation we are going to use. So for substituting the value of ns, first we have to find the value of ns. So ns is obtained by capital Ns, that is rpm by 60. So we are getting the small letter ns as 3.125 rps, and the number of poles p. Okay, same equation, that is ns equal to 120 f by p. So p is equal to 120 f by ns. F we know, capital Ns, that is rpm, it is given, and we are getting the number of poles as 32, and here we can assume the winding factor as 0.955. okay, and initially we are going to find the output coefficient C0. The equation is 11 kW BAV AC into 10 raised to minus 3. Okay, so C0 we will obtain it as 214, and D square L, using the same equation D square L, we are getting it as 3.74 meter cube. Okay, and for separation of D and L, it is given that L by tau is 0.65, and we know the tau is, the equation for tau is pi d by p, that is pi d by 32. okay, so it is substituted here, you can see substituted here, and L is we are getting a relation between L and ds. L is equal to 0.0638 d. okay, and just substitute the value of L in this equation D square L, and we will get it as 0.638 d square is equal to 3.74, and from that we obtain the value of d as 3.9 meter, and substituting the value of d in this equation, we are getting L as 0.245 meter, and we have to check what type of pole construction is to be used. Here the peripheral, so for that we have to find the peripheral speed first. So VA is equal to pi dns, and we all know the values of d and ns. So we are VA, the peripheral speed is 38.2 meter per second here, and also it is given that the runway speed is 2 times the peripheral speed. okay, 2 times the peripheral speed. So we have to calculate the runway speed also for understanding the stability of the machine. okay, so the runway speed can be calculated as 2 into VA. okay, 2 into A. So runway speed will be equal to 2 into this 38.2. okay, 38.2. so it is we will get the answer as above, okay, approximately above 550 meter per second. okay, above 50 meter per second. So here the correct value is 3.2 into 2. okay, we will get it as 76.4. okay, 76.4 meter per second. So it is above 50 meter per second and below 80 meter per second. So here in between 50 and 80 we are using dovetail construction. okay, dovetail construction for poles. okay, so that's the question. I hope it's clear. So thank you. So do it.